In Chapter 8, we'll be looking at making alkenes via elimination reactions. You can see there are several alkenes in nature that occur. We'll see limonene later in the semester. We'll extract that from oranges, and that has two double bonds, or alkenes. Cholesterol is a steroid that contains one alkene, and that's produced by all animals as well as humans. Allicin, which is part of the odor of garlic, has alkenes. And we can see geraniol, which is used in perfumes, and that comes from roses. Beta-farnesene is another alkene that has several double bonds here. There's 4. Alpha-farnesene is found in the natural waxy coating on apple skins. Petroleum is used to make several alkenes. It first makes ethylene, which can then be converted to several of these different components. So acetaldehyde, acetic acid. Vinyl chloride can be made from ethylene dichloride, which is made from ethylene, which makes PVC, or polyvinyl chloride, which we've seen in piping, ethylene oxide, and ethylene glycol. So all of these compounds can be made from alkenes. So it's a very versatile starting material. When we name alkenes, they're named using the same procedure as we used in Chapter 4 with alkanes, except we modify a couple of things. The main one is the beginning parent chain. So our parent chain has to include the carbon-carbon double bond. So on the structure here, even though it looks like the longest parent chain is 1, 2, 3, 4, 5, 6, 7, we have to have our longest carbon chain include the alkene. So this would actually be our parent chain here, which ends up being 1, 2, 3, 4, 5, 6 carbons. So our parent is 6 carbons on this particular alkene. We then identify and name the substituents. So we have an ethyl group, and we have 2 methyl groups. We then assign a locant and prefix if necessary to each substituent. The carbon-carbon double bond should have the lowest number possible. So this is 1, this is 2. So our ethyl group is at 2, and our methyls are at 5 and 5. Then list them as we did before in alphabetical order. And then we can place the carbon-carbon double bond just before the parent name or just before the -ene suffix. This would be 2-ethyl, 5,5-dimethyl, 1-hexene. Or 2-ethyl, 6,6-dimethyl, hex, 1-ene. So either of those are correct. If we were naming this substituent, which is numbered here, so the carbon-carbon double bond gets the lowest numbering possible. This one ends up being 5,5,6 trimethyl 2-heptene. Or hept 2-ene. If you have a cyclic structure, your carbon double bonds have to be between 1 and 2. If I start numbering with the 1 on the bromine, and that being 2, this allows the bromine, which is alphabetical, to have the lower numbering. Additionally, if I started this here, this would be 1, 2, 3, 4, 5, 6, which would be even lower than the 1, 2, 3. So this would be 1 bromo, 2 ethyl, 3 methyl, cyclohexene. You can do 1 cyclohexene or cyclohex 1-ene, but if it just says cyclohexene, then it's automatically assumed that the carbon double bond starts at 1. On this one here, 2, 3. This has 7 carbons and there's 2 double bonds. 1 substituent, so we have 2-methyl. And then we're going to list where each of the double bonds start. So this would be 2, 5, hepta, diene. So that di tells us there are 2 double bonds there. The 2 and the 5 tells us where those start. And the other version of this would be 2-methyl, hepta, 2, 5, diene. Either of those are correct. We can have isomerism in alkenes. In this group here, both of the substituents are on the same side of the double bond. So this is cis 2-butene. They're both on the top side of that double bond. And here if I cut the double bond in half, one is on the top and one is on the bottom. This is trans 2-butene. And then we have cyclopropene, cyclobutene, cyclopentene, cyclohexene. So for these pi bonds to remain intact, we can't rotate around the double bond. And in cyclic alkenes with less than 8 atoms in the ring, you can only have cis alkenes. You wouldn't have a bond such as this to get that in there. That's trans. Cyclic ones are always going to be cis. We cannot always use cis or trans to determine the isomers on alkenes because there can be more than 2 groups. The cis and trans should really only be used when it's the same groups coming off of there. So what we use instead, which is synonymous to R or S, is E or Z for stereoisomers. So what we do is we prioritize the groups attached to the carbon-carbon double bond, just like we did with stereoisomers for R and S. That's based on the atomic number. If the top priority groups are on the same side of the carbon-carbon double bond, it is Z, or zusammen, which means together. And if the top priority groups are on opposite sides of the carbon-carbon double bond, it is E for entgegen, which means opposite. Those are German words, and that's where the E and the Z came from. So if we look at the first compound here, I'm going to cut the double bond into 4 quadrants. So I'm going to first focus on this carbon right here. And if I look at this carbon only, I'm going to look at what is above and below the double bond. Which group here is larger? I'm going to look at the atomic number. Carbon is 6 and fluorine is 9. So this is the larger group on this carbon. If I look at this carbon now, I'm going to compare groups by atom number again. So I have hydrogen versus nitrogen. Nitrogen is larger than hydrogen. So I've now looked at my carbons separately, and now I'm going to look at the double bond. What you can do is if you lay your pencil over top of the double bond and cover it up and look at where your circles are, they're both on the same side of the double bond, which is down here. This one is Z. I'm going to do the same thing with the next one here. Compare the first carbon. It's carbon versus F. F is the winner. I have this carbon. It's N versus H. N is the larger one here. If I lay my pencil across the double bond, now the groups are coming off of the opposite sides of my pencil or pen. So one is coming off the top and one's coming off the bottom. So this one is E. So let's look at one more example. Look at the first one here. So I have a carbon, 2 oxygen, or 3 carbons. So even though 3 carbons molecular weight-wise weighs more than the oxygen, we're looking at the atom that's connected to. So this is going to be the oxygen. This is my large group. On this one here I have C. These two are the same. This is a carbon to 1 carbon, and this is like carbon to 2 carbons. So this is my larger group here. So you lay your pencil up on the double bond, and one group is coming off the top, one is on the bottom. This one is E. There's 2 double bonds here. So if I look at this double bond, I'm going to compare these groups here. And those 2 are the same. So this one is neither E or C. There's no isomers possible on that one because it is a terminal alkene and it has the same 2 groups here. Okay, so take a minute to practice these problems and see what you get. So on this carbon, it's carbon versus all of this. Carbon versus Br. These are on opposite sides. This one is E. Here we have a CH3 and a CH3. Because these 2 groups are the same, this is a neither. It's this group and this group. This one is also E. Because of steric strain, cis isomers are generally less stable than trans isomers. So we can see the trans 2-butene. These methyl groups are very much out of the way of each other, but there's a lot of steric strain and overlap in the cis 2-butene. So what you're going to see here in Alkene Stability, the most substituted alkene, which has 4 groups coming off of it, is the most stable. This is a tetrasubstituted. That means there's 4 substituents coming off of the double bond. The next stable is a 3 or tri-substituted. Then we have di-substituted in the trans. And we have di-substituted in the geminal. So this still has two groups coming off of it, but they're both on the same carbon. And then we have the di-substituted with cis, and then mono-substituted. This one is least stable. Here's another practice problem. Give the IUPAC name of each alkene and then determine if it's mono-substituted, di-substituted, tri, tetra, etc. So this one here, we're naming this as, we can do 1, 2, or 1, 2. Isopropyl is first in the alphabet, so I'm going to choose this to be 1. This would be 1 isopropyl, 2 methyl, cyclohexene. Here we want a number to give the alkene the lowest numbering. This would be 5, 5 dimethyl, 1, 3 hexadiene. And if we really wanted to be correct here, we would do 3E. And that's referring to the double bond. There is an E double bond or trans. The other thing we want to look at is to see what the degree of substitution is. This double bond here has 4 groups coming off of it. This one is tetrasubstituted. This first one here has only 1 group coming off of that, so this is monosubstituted. And that one there is disubstituted. Now we can start moving into elimination reactions. In an elimination reaction, a hydrogen and a leaving group is eliminated. So the carbons stay where they are, and we leave a double bond in its place, in addition to the hydrogen and the leaving group. And elimination involves a leaving group, a base, not a nucleophile, and a beta hydrogen that's next to the leaving group. So all eliminations are going to involve both the loss of a leaving group and also a proton transfer. The mechanism can be one step or it can be stepwise. And the beta hydrogen is a hydrogen on the carbon adjacent to the leaving group. In the one-step reaction, we have a base that goes fishing for that hydrogen. It takes the electrons here, so this is a proton transfer arrow. And then those electrons go to form the double bond while it kicks off the leaving group. So this is the loss of leaving group. So the carbons stay where they are, and we form a double bond plus the leaving group minus. And you can also draw here the base with the hydrogen. In the two-step reaction, we get the loss of the leaving group, which forms a carbocation. And then we have a base. Which can grab that hydrogen, and those electrons go to form that double bond. So this is a proton transfer, that double bond, plus base H. So it's all about that base. In the E2 reaction, it's an elimination, which is what the E stands for. And 2 is bimolecular, just like in the SN2. This one is synonymous with the SN2 in that the rate is dependent on the substrate concentration and the base concentration. In SN2 reactions, it was substrate and nucleophile. In E2, we're looking at the base. There's a base that pulls off the proton after it's gone fishing for it. Those electrons between the carbon and the hydrogen go in to form the double bond, and it kicks off the leaving group. So proton transfer, and then loss of leaving group. The base will take the proton as the leaving group leaves. It's a one-step reaction. Tertiary substrates are more reactive towards E2 than our primary, even though it's more sterically hindered. The tertiary substrate should go through a more stable transition state, which is favored. Tertiary substrates are more reactive towards E2, even though the primary ones are less hindered. We can see the potential energy diagram here. We start out with the OH minus, which can grab a proton. This is the transition state that it goes through, and then we end up with the alkene there. Regioselectivity. This is something that occurs if there's multiple reactive sites or regions on a molecule. Multiple products are possible. In elimination reactions, there are often different beta sites that could be deprotonated to yield different alkenes. What this is saying is we have a bromine on the alpha carbon, and for an E2 reaction, we're removing a beta proton, so a proton next to the alpha carbon. And here we have two different types. This would also be considered a beta proton, but this is B1, this is B1. We'll call this one B2. If I do a reaction in where I extract B2, I have a base, and it's going to grab the H from the B2. Those electrons come in here and kick that off. I'll get a double bond here. This is called the Zaitsev product. If I have a base here, and I pull off beta 1, those electrons go into here, and that kicks the bromine off. And the double bond forms here. This is the Hofmann product. This is a tri-substituted alkene. This is di-substituted. This has 3 groups coming off of it. This has only 2. This is the more stable product. We learned a few slides ago that the tri-substituted is more stable than the di-substituted, and that's why that is the more stable product. Depending on what base you use, you'll get different ratios of these products. This is the Zaitsev product. This is the Hofmann. If you use ETO minus or ethoxide, 71% of your product will be Zaitsev product, 29% will be Hofmann. If you use tert butoxide, you will have 28% versus 72%. If you use this big guy, which looks like a tert butoxide except it has extra carbons, it is 8% here, 92% here. So potassium ditert butoxide, diisopropylamine, trimethylamine. These are different bases that you can use. And one thing that you may observe is this is a small base, which favors the Zaitsev more stable product, and these are bulky bases, which prefer the Hofmann product. If you have a small base, it will be considerate and think about what will be the most stable alkene, and it can take its time and find the proton to pick off that will give you the most stable alkene. A big bulky base just wants to get in there and grab any proton, and it wants to grab the one that's easiest to get to, which is one of these end ones, to give you the less stable product. Small base favors Zaitsev. A bulky base will favor Hofmann. Okay, so predict the major product for each of the following E2 reactions. I have this bromoalkane. There's T-butoxide, which is the same thing as this. And I have sodium ethoxide. So if I go this route first, if I look at my hydrogens available, I have a beta or a hydrogen here, HA, and there's one here, HB. With T-butoxide, this is bulky. So that's going to grab the most accessible hydrogen, which is HA, and that one's the one on the end. Those electrons go in there. So my bromine is gone, and I've now formed the double bond there. This is the Hofmann product. This is a small base, so it's going to grab the proton that will give it the most stable alkene. So that will be HB. This is the Zaitsev. So tri-substituted versus mono-substituted. And again, we can control that by using the size of the base.